For Physics Lab 4, it was mostly centered around oscillations. The purpose of this lab was to investigate the oscillatory motion of a spring mass system and to compare the model versus experimental data, as well as test energy conservation and determine the oscillation period. The overall goal was to determine if the model follows the energy principle we identified in class. And it was observed, the main result was observed that the system's total energy remained constant at 0, demonstrating the energy principle. To break down what the system was, it was the spring plus the ball attached to it plus the earth. And the surroundings was none, therefore the work done by the surroundings is 0, as well as the change in energy is equal to 0. So this demonstrates a conservation of energy. Here are two diagrams showing the two different forces acting on the object, like in its stretched spring component form and its compressed spring form. So as you can see with the stretched, the force of gravity and the force done by the spring is in opposite directions, but compressed, they become the same direction. Here are some of the fundamental principles we use in labs. This includes the velocity update, position update to make sure that we're constantly updating based off of it. And we also have kinetic energy, which we're going to use in our energy principle formula, as well as the gravitational potential energy inside the system, which is just going to be m times the mass times the gravity times, which is just going to be changed in y. And then the spring changing potential energy will be 1/2 k times s final squared minus s initial squared. S is basically the L, which is going to be the current length minus the relaxed length. So that's what that stands for. And then the whole conservation of energy principle is just the fact that the change in energy is equal to work done by the surroundings. And in this case, work done by the surroundings is equal to 0. Therefore, we know that the change in energy plus the change in gravitational potential energy plus the change in gravitational spring energy is going to be equal to 0. When setting up the tracker, we determined that we use a calibration of 0.7 meters, and we set our origin at the top of the spring, on top of where the spring is connected to a fixed surface. The initial conditions after setting up the experiment were set to be with the ball mass was 0.402 meters, the initial kilograms, the initial position was set to be negative 0.05 in the x direction, negative 0.8 in the y direction, 0 in the b direction, meters, and initial velocity was set to be negative 0.052 in the x direction and then 0.2105 in the y direction, meters over seconds. Delta T was initially 9/200, which was determined from the frame rate of the video, but then later it was adjusted to be 10/1000 to account for any weird changes in the energy, because initially my model was finding energy to the system when it shouldn't have. L was also 0.7 meters. When creating our computational model, we were determining what the oscillation period was going to be, which we know is equal to 2 pi times the square root of mass over the stiffness of the spring. And to find what T was, I did 1/3 over I took the time differences between 3 of the peaks of the y graph and divided it by 3 to get the average time, which was 1.524 seconds. Then I calculated what the spring stiffness K was equal to, which when you rearrange the equation above, gives you 4 pi squared times mass over the oscillation period squared. And I got 6.853 newtons over mass. And so we used all of that to calculate what the rested spring length was, which is going to be F net equals the spring force plus the gravitational force. And when you recalculate that, we know that F net is equal to 0 in this case because the ball is at rest. No, because we know that the spring force and the work done on the system, this is the rested spring length, we know that F net equals 0. And so spring force plus the gravitational force is going to be equal to 0. So when we recalculate that, we got L minus mg over k, which is equal to 0.1234. And we plugged all those values in the equations here, which we just put from the formula sheet. And we calculate kinetic energy was 1/2 m speed squared, and then I explain it here. And then the universal gravitation potential energy is equal to mass times gravity times the position. And then the change in the spring potential energy is going to be 1/2 times k times s squared. And E is just going to be all those together. So that's cool. And then we use Newton's second law to calculate and update the position and velocity. So those are our main fundamental physics principles. And so our results showed this graph, which shows the change in energy versus time. We see delta K with the purple, and we see that it oscillates around 0, becoming 0 when potential energy, which is either the red or the green, is at its max or min, which makes sense because they're opposite in terms of when kinetic energy grows, potential energy decreases. When potential energy that is max, kinetic energy is. And then for universal gravitation and spring gravitation, we see that there's the main energy exchange between those potential energies, as well as the change in energy is flat and on the 0 axis, showing that energy is conserved and it doesn't change at a constant. And we also see that mass moves relatively slow compared to a large amount of potential energy stored in the stretch. So kinetic energy is slowly going to get slower. So that's why we see it's decreasing in amplitude. To further analyze our results, we compared the model versus the experiment in terms of what we observed versus predicted in position versus time. So first, to talk about the x position versus time, we see that most of the data points are relatively lined up, which makes sense due to the fact that it was very accurate timing. We made the x very accurate. But in terms of the y position versus time, it was very difficult for me to get both of these graphs to be accurate at the same point, which could mean that causes of possible potential errors could be calculating the spring constant only using the y position data from the tracker, or an issue with accuracy of the tracker data, which is just when I was pressing the points. So you can see that the y position versus time gets more accurate towards 5 seconds, and then it's the most accurate for x near, I think, 2.5 seconds. So this could just be up to human error as well, because this graph was pretty accurate. Now to speak more on, so we used these models and we were able to see if the energy principle was satisfied. We saw specifically that, yes, it was satisfied, because the energy principle says that we see that the change in kinetic energy and the change in gravitational potential energy and the change in spring potential energy is all equal to 0, which makes sense because the change in energy is equal to those value changes. We see that the system includes the ball, spring, and the earth, so there will be no external force acting on the system, which is why that equation holds true. Next, to answer a couple other questions of analyzing the differences between the oscillation periods for the y direction and the x direction, the time for 3 oscillations in the y direction is equal to 4.572, and when I divided this by 3, you get t, which is 1.524. This is what I used in my experimental code. Next, I did the x direction, so the time for 3 oscillations in the x direction, which is going to be like taking the points between 4 peaks, is going to be equal to 4.953 seconds, divided by 3 is 1.651 seconds, and as you can see, the numbers are different by at least, just like off the top of my head, at least 0.1 seconds, and these results differ, leading to discrepancies. So these could be due to discrepancies with the spring constant. So when these answers are different, they're going to change what k is equal to, since k is calculated based off the oscillation period. And so because of that, that's why we could see some errors with these results as well. This can be fixed by averaging the times or averaging the spring constants to get a more evened out oscillation period or a more evened out spring constant. Okay. In conclusion, it was observed that the system's total energy remains constant at zero, demonstrating the energy principle to be true. Thank you.